In this video, we're going to look at sums of vector subspaces. Suppose that V is a vector space and U and W are subspaces of V. Then U plus W represents a sum of all the vectors in U and W. Now, this is not a union, but it's like kind of like adding together all the vectors in U and W. So like, let's take an example. Suppose you have a vector space V is equal to X, Y, Z, W, such that X, Y, Z, W are in the reals. So the vector space is basically R4. And also, suppose we have subspaces, say U, which is of this form, so it'll be four-dimensional vectors except this entry 0, and so is this one. And you have, say, this subspace. And where there'd be something in the X position, the Y position, these two be 0. Again, the components are all from the real numbers. And of course, again, remember, you can show that these are subspaces. And now, U plus W will be summing all of these vectors with all of these vectors. And so what would you get? You would get a set something like this. Let's see, we would have an X right here with me. We'd have all the possible values here. We'd have Y. When we add these two together, we still have zeros in the Z position. And W. So this is X, Y, W in R. Like this. And so that would be the sum. So once again, notice this is different from the union. The union would have just all of these vectors and all of these vectors. But here, with the sum, we're adding them together. So now also, it's important to notice that even though we're adding the individual vectors together, we'll still have all the vectors from U in this set. And we'll have all the vectors from W in this set because we're going to be adding 0, 0, 0, 0, 0 to all the vectors in W. So we'll still have all of these in our set. And then we're going to add 0, 0, 0, 0 to all the vectors in U. So we're going to have a U in the set. So that's called a direct sum. Oh, excuse me, that's called the sum of these two vector spaces. Now, a direct sum is a little bit different. Let's take a look at that. So let me say this. Suppose B is a vector space. And say U1, U2, up to UN are subspaces. then we say V is a direct sum, not just a sum, but a direct sum of our subspaces U1, U2, UN, if for each vector V in our space V, we can write V equals small u1, u2 plus un uniquely at the sum, again, where u1 is in our subbase capital U1, U2 is our subspace capital U2, UN, their capital subspace UN. So it's called a direct sum if every vector in V can be written uniquely as a sum of vectors from each of these spaces here. That's the definition of a direct sum. And I should say something obvious here. And let me put this in parentheses, obviously. And then let me just say one more thing I should say. It's a direct sum, and direct sums are written this way. Are written as V U1, U2, plus UN. So again, if every vector in V can be represented uniquely as a sum of vectors from these subspaces, then this is called a direct sum. It's written this way, where you have a plus with a circle around it. And what I was going to say a minute ago, obviously, if you have a direct sum, this implies that V is equal to the sum of these subspaces. Like this. Now, of course, this sum does not imply direct sum, but a direct sum does imply this, because this just means that every vector in V can be represented by a sum of vectors from these subspaces, but this does not imply uniqueness. The direct sum implies both that you can get the sum of each vector in V, and that's unique. So let's look at some interesting theorems related to these. And I'll just call this theorem 1. Suppose V is a vector space. And U1, U2, UN are subspaces of V. Then we have a direct sum. V would be equal to the direct sum of these subspaces. If and only if we have these two conditions. A, V is equal to U1 plus U2 plus UN. We need that condition. And B, zero equals U1 plus U2 plus UN. Once again, each of these small u's are from each of these subsets, subspaces. So U equals this if and only if each of these u's is 0. So this is a handy way to determine that you have a direct sum, because trying to find, trying to show something as a direct sum is very difficult, because again, you would have to show that every vector V can be represented uniquely as a sum of vectors from each of these. And so that's be kind of hard, but if you can show these two things, you're done. And so let's prove that this theorem is true. So again, we'll go the first way. Suppose that we do have the direct sum. Then, as I mentioned previously, if you have this, you automatically have the sum part. Then because by definition, you have to have that sum. So therefore, A is proven. Now to try to prove B, since every vector in V, in our subspace V, is represented uniquely so is 0 in V. It's going to be represented uniquely as, members of each of this set. That is like this. So you're going to have that that's true. But of course, this is going to be true when 0 and let me say this part. Let me say this is going to be true when U1 is 0, U2 is 0, UN is 0. But since it's unique, then that's the only way they can be represented, because remember, this U0 is going to be represented uniquely, and we know that you will get 0, this equal to 0 when these are 0. And because, once again, because these are subspaces, we know that 0's in each of these. So therefore, that's the only way this can be represented. So therefore, that proves part B. So let's go in the other direction now. Let's suppose that these two are true. Suppose A and B hold. Again, remember A and B, that we have this V is equal to the sum, and we can get 0 only when all of these are 0. And so pick a vector in V, and we want to eventually show that this is going to be represented uniquely. Then V is going to be equal to U1 plus U2 plus UN by A. Because remember, because we have this sum, we know that we can represent every vector in V by a sum of vectors from each of these. So this is true by A. And let me give this name this equation name. Call this equation 1, because we use them at. Suppose there's going to be another representation. Suppose we can also represent V by, say, some other vectors from each of these sets. So let me call this U11, U12, U maybe 1N, just to represent them differently. Once again, where this is from subspace 1, this is from subspace 2, etc. Let me give this an equation number. Equation 1. Excuse me, equation 2. So now subtract, and you probably do it in either order. Let me subtract equation 1 minus equation 2. And so when we subtract them, we're going to get 0 on the left-hand side. And we're going to get this on the right-hand side. This. Now remember, again, we look up here, these were both in the subspace U1. So let's just mark that. Those are in U1. And this one was from here. That was in the subspace U2, etc. All the way up here. This was in the subspace UN. But by B, and remember B said U was represented as this sum if and only if these are all 0. So the element from subspace 1 was 0, subspace 2 was 0, these were all 0. So by B, this is saying that this has to be 0. 0 is only represented by a 0 from here. Same thing over here. All the way up. And then, of course, this implies U1 is U11, U2 is U12, UN is U1N, like that. And so that means that equation 2, which was supposedly another representation of a given vector V, we represent this way, but actually this U11 is equal to U1, same as this. U12 is equal to U2. So the representation was not unique, but this representation was exactly the same as this. So therefore, for any vector, we just picked the typical vector in V, and we were able to show the representation was unique. Therefore, V is equal to a direct sum of those subspaces. So again, that's a handy theorem to keep in mind. We call it here theorem 1. It's handy to keep in mind because it's an easier way to show that you have a direct sum. So let's try another theorem. Let me just give this call this theorem 2. And suppose U and W are subspaces of V, of some vector space V of vector space. Then V is equal to the direct sum of U plus W if and only if we have, once again, A, V is equal to the sum of U plus W, and B, the intersection of U plus W is the zero vector. Again, it's very similar to a previous theorem. We said that, V was the direct sum of these subspaces if they were first the sum of the subspaces, which same thing we have here. But for the second one, for B, we have something a little bit different. The intersection of these two subspaces is zero. Now, once again, this only applies when we have exactly two subspaces we're working with. So let's see if we can prove this. Once again, we'll go the one direction. Suppose that we have the direct sum. V is the direct sum of U and W. Then V is equal to U plus W. Again, we said before, obviously, the direct sum implies a sum. Therefore, that proves part A. And so the next, consider a vector V in the intersection of these two. So we have V in this intersection. Then, since U intersection W is a subspace, remember the intersection of two subspaces is a subspace. Then the additive inverse is in there by definition of a subspace. Negative V is in this intersection. But of course, V plus that minus V is zero, or if you want to write it this way, zero is in V plus minus V. And now, since every vector in V is represented uniquely, so is zero. So since zero is represented uniquely, this has to be zero, and this has to be zero. V is zero, and negative V is zero. Therefore, V is 0. And V was in this intersection. So U intersection W has to be 0. So in this part right here, remember every vector in V has to be represented uniquely by something from U and something from W. That's what makes this part true. And again, this was, we had V, and so V plus minus V, then we have to have then that this is 0 and this is 0. This is from U and this is from W. And so this is true. And that was, therefore, we have B. Now let's go in the other direction. And let's see. This time we're going to assume, so suppose we have our two things. We have our A and B. Suppose we have A and B, which says V is equal to U plus W. And the intersection of those two subspaces is 0. So suppose we have this time. Now, remember, what we want to do is we want to show that the vector is going to be unique. So first of all, let 0 equal U plus W, where U is in U and W is in W. Then from this, of course, then this is going to apply U equals negative W. Now, since U, the capital U, the subspace U and W are subspaces, then since W is in W, it's a subspace, its additive inverse is also going to be in W. Like this. And now, of course, therefore, U is going to be in W because U was equal to minus small w, and it's in W, so that means U is in W since they're equal. So therefore, what we have here, we had U is in U, and U was in W. Therefore, U was in U intersection W, but U intersection W was 0 by part B, which we had up here. So that means that U is 0. So now once again, so we have established so U's in W, and therefore, because we had let 0 equal to this, so U is equal to 0, and W has to be 0 from up here. So that means, so again, what this implies is, this means zero equals U plus W implies U is 0 and W is 0. So now we're going to use this to prove uniqueness. Again, let V be a typical vector in V. Then V equals U1 plus W2, where U1 is in U. And let me call this, sorry, let me call this W1 here, please. And W1 is in W. And assume also that there's another way to represent this. Remember, we're eventually going to show that this can be represented in only one way. And similar to what we did for the proof for the previous theorem, we call this equation 1, equation 2. So now, once again, subtract. When we subtract the left-hand side, we get 0. And once again, remember, this was in U, because remember, these are both in U, so their difference is going to be in U. And this is in W, subspace W, because each of the W1, W2 are in W, and then their sum or difference also has to be in W. But from this up here, and let me give that a name, let me call that equation A. But by equation A, and actually let me give it a different name altogether, because I will use A and B. Let me call this equation star. So by equation star, remember we set up here, if you have 0 and you have this sum, implies that each of these has to be 0. By equation star, this has to be 0. And this has to be 0, which implies U1 equals U2 and U1 equals W2. So this sum is unique. We tried to find a different representation, but realized when we go through this, showed that it was exactly the same. And then therefore, V is a direct sum of U plus W. Again, those two theorems are good to have handy. They can be very useful and easier ways to show something's a direct sum. And also, the techniques in these proofs come up often, so it's good to understand how these proofs work.